Okay.
Okay. Good afternoon, good morning, and good evening to everybody. So today we have the section 46 of our seminar in Seminario De Edp y Matematica Aplicada, organized by several universities in South America and in Europe. And today we have two excellent speakers, Professor Vicentiu Radulescu and Professor Alberto Mercado. And to introduce Professor Vicentiu is going to be introduced by Professor Damião Araújo, and Professor Alberto Mercado is going to be introduced by Professor Mauro Rincon. So you have the word, Professor Damião.
Thank you, Diego. So it's a pleasure to introduce Professor Vicentiu Radulescu. He is a specialist on partial differential equations, nonlinear analysis, and calculus of variations. So his affiliation is AGA, University of Science and Technology, Krakow, Poland. The second affiliation is University of Cracovia, Romania, and Institute of Mathematics of Romanian Academy in Bucharest. So he is going to talk about a new phenomena in the study of double phase problems. So Professor Vicentiu, so thank you for coming, and it's yours.
Thank you very much for your introduction and for inviting me to give a talk in your seminar. So I shall start with an outline of my talk. At the beginning, a motivation and some pioneers of the field. The first direction I shall discuss is a striking discontinuity property of the spectrum in the case of double phase problems. This is a result obtained in collaboration with Nicolas Papageorgiou and Professor Repos from Ljubljana. And I shall continue with the result obtained in collaboration with Claudianor Alves about double phase problems with mixed regime. This is a new research direction with plenty of very interesting open problems. And I shall conclude with some perspectives in this direction. So the main result will concern the isotropic case. In this direction, I shall discuss about this discontinuity property of the spectrum. And in the anisotropic case, I shall discuss about problems with the mixed, subcritical, supercritical, critical regime. So at the very beginning, just to explain the main idea, one of the basic ideas of this talk, I shall start from the very classical eigenvalue problem for the Laplace operator minus Laplace of u equals lambda u in a bounded domain with smooth boundary in Rn with u equals to 0 on the boundary. So as we know very well, all of us, this is a basic result. The spectrum of the Laplace operator is discrete in the sense that its spectrum consists of an infinite family of strictly positive eigenvalues, and which is also unbounded, this sequence of eigenvalues. This is very, very well known. So the main question here, so Laplace operator, this is recalled here. The main question here is to start to look again at this eigenvalue problem, very classical, and to see what happens if we consider in the left-hand side an additional differential operator, for instance, a p Laplace operator. What we can say about the spectrum of the new problem. That is why I shall consider the new eigenvalue problem minus Laplace of u minus p Laplace of u equals lambda u. So we keep the basic eigenvalue problem, the linear one, and we add this quasi-linear operator. Of course, we keep the boundary value condition. Here, P Laplace of U, of course, it is the divergence of modulus of gradient of U to P minus 2 gradient of U. Anyway, both eigenvalue problems, the starting one and the second one with this kind of perturbation, are associated with the study of some Dirichlet energy functionals. The first one is a standard energy integral over omega modulus of gradient of U squared dx, while the second one, which appears here, is integral gradient of U squared plus gradient of U to the power P dx. So we see here for the first time the so-called double phase energy, in the sense that under the integral sign, there are two different powers of the gradient term. Concerning the beginning of the study of problems of this type, to the best of my knowledge, it was Zhikov who studied energy functionals of this type in relationship with models arising in mathematical physics, for instance, Lavrentiev phenomena. In fact, Zhikov studied three types of energy functionals. The first one, which appears here, is associated with the standard linear Laplace operator. The second one is associated with the px Laplace operator. And the last one is really a double phase energy, because we find the contribution of two terms, gradient of U to P plus gradient of U to Q, subject a modulating coefficient, the potential A of x, which is greater or equal to 0. So in the first part of my talk, I shall discuss about this isotropic model. And in the second part, I shall consider problems involving the px Laplace operator, which is defined here. The mathematical theory of double phase problems was initiated in several seminal papers by Marcellini and Mingione, who were mainly interested in the study of regularity properties of minimizers of these energies. In fact, Zhikov showed that the regularity of the variable potential P of x is essential in order to have or not the density of smooth functions with compact support. Otherwise, we obtain the Lavrentiev phenomenon. You see here, for instance, if we have logarithmic Hölder continuous potentials, which are defined here, then we don't have any problems. We have the density of smooth functions. Also, in the same situation, we have the Poincaré inequality. In my case, I shall always assume, when I discuss about variable potentials, that P is smooth enough. Otherwise, a very interesting open problem is to see what happens, so to study related problems, related models, but when P is not very smooth, when we have really the Lavrentiev phenomenon. In the case of potentials of this type, we have some this embedding, but this is not really of our interest. Concerning the function spaces with variable exponents, so the equivalent of Lebesgue and Sobolev spaces, but with variable exponents, so P is replaced by P depending on x, there are some strange phenomena. For instance, we don't have this co-area formula, which holds if and only if P is a constant function. In the case of variable exponents, we don't have something like this. LPX spaces, so Lebesgue spaces with variable exponent, do not have the mean continuity property, which is explained here. Also, the function spaces with variable exponent are never translation invariant. And the use of the Young inequality is very limited, in the sense that this inequality holds if and only if P is a constant function. And as we said, we also have Lavrentiev phenomenon, provided that P is not smooth enough. Another motivation comes from this situation, in the sense that double phase or multiple phase operators are used in some circumstances to approximate some classical differential operators appearing in mathematical physics, but without a good variational structure. For instance, the Born-Infeld differential operator, which appears here, can be approximated via Taylor expansion formula, which appears here, and taking the first order approximation in the Taylor formula, we observe that we can approximate the Born-Infeld operator with this linear operator minus Laplace of u minus 4 Laplace of u. And also we can use a multi-phase differential operator, which appears here. So now I shall discuss about the first problem, namely the structure of the spectrum for a double phase problem, a very classical double phase problem. So the idea is the following one. I shall start from the eigenvalue problem for the Q Laplace operator, which is stated here. So for instance, at the very beginning, we assume that alpha equals to 0. This first differential operator doesn't appear. And we consider this is a standard eigenvalue problem for the Q Laplace operator, but we add a second quasi-linear operator, which is a P Laplace operator. So the question is to see what is the spectrum of this new nonlinear eigenvalue problem, provided that alpha and beta are positive constants. Here, maybe a very interesting question is to see what happens if alpha and b are not necessarily positive, to try to study the relationship. For sure, there are new other phenomena which can appear. To illustrate what happens here, let us consider a very simple example. For instance, we consider we take a convex combination in the left-hand side. This means that we fix beta between 0 and 1. We take alpha equals to 1 minus beta. All depends on beta in this situation. We denote by L beta the differential operator in the left-hand side of this problem, and by sigma of beta, the spectrum of this one. The main result of the first part of my talk will show that the spectrum consists of an open interval, which is obtained as follows. Lambda 1 of Q is a principal eigenvalue of the Q Laplace operator, so the smallest eigenvalue of the Q Laplace operator. We multiply by beta, so this is a crucial value, beta lambda 1 of Q, and we go up to infinity. So we obtain an open interval. What happens here if we are looking what happens, for instance, at beta equals to 1? At beta equals to 1, we observe that in this situation, alpha equals to 0. So this one disappears. So for beta equals to 1, we obtain exactly the spectrum of the Q Laplace operator. But we already know that this is isolated because the smallest eigenvalue is isolated. So this means that we obtain really a discontinuity property of the spectrum. Why? Because if we take here beta equals to 1, we obtain an open interval. But on the other side, we obtain something which is not an open interval. To illustrate better, we can consider the linear case, which corresponds to Q equals 2. So again, from one side, we obtain an open interval. From the other side, for beta equals to 1, we obtain this time the spectrum of the standard linear Laplace operator, which is discrete, which consists of a family, of a sequence. Some facts, very well-known facts about the linear eigenvalue, the quasi-linear eigenvalue problem for the R Laplace operator. We know that the smallest eigenvalue is isolated in the spectrum. It is also simple, and also it admits the following variational characterization, which is given here to minimize the standard Rayleigh quotient, which is defined here. Very well. Our problem has a variational structure, so it is natural to associate to our equation the energy functional, which is defined in this way. R is the maximum between P and Q. So the first two terms correspond to the left-hand side and to the source term, while the last one corresponds to the reaction term, to the right-hand side of our problem. In this situation, working on the whole space is not a good idea because we do not obtain a good information. That is why it is natural to associate the Neha manifold to this functional, which is a set of functions u in W1R 0, such that phi prime of u applied to u equals to 0, of course u different to 0, and to consider to analyze the energy function with respect to the Neha manifold. As until now, we shall denote by sigma of alpha and beta the spectrum of the differential operator arising in the left-hand side. Very good. So the main result of the first part of my talk shows that the spectrum here consists of all the values strictly bigger than beta lambda 1 of Q. So again, I repeat, lambda 1 of Q is the smallest eigenvalue of the Q Laplace operator. So in this case, multiplied by beta. The main ideas of the proof are the following one. The case where Q is less than P is simple because the associated energy is coercive. So we apply standard methods, for instance, the direct method of the calculus of variations. The difficult case is when P is less than Q. In this situation, the energy functional is not coercive. So the main idea is to minimize the energy, but with respect to the Neha manifold, not with respect to the whole space. And we obtain some intermediary results. For instance, this characterization of the Neha manifold, very interesting. So the Neha manifold is not empty if and only if lambda is strictly bigger than this crucial value beta lambda 1 of Q. Then it is natural to define the infimum of the energy with respect to the Neha manifold. So M lambda is denoted by M lambda, this infimum. Now, using the definition of the Neha manifold, we obtain this energy estimate simply by using the definition and replacing this information, this energy estimate, in the expression of the functional. We obtain, in fact, that the energy functional phi lambda equals alpha times 1 over P minus 1 over Q multiplied by the norm, LP norm of gradient of U to the power P. On the other hand, we observe that by our hypothesis, P is less than Q. So this is strictly positive. Here you see we use the fact that alpha is strictly positive. So this implies from one side that the infimum M lambda directly from here is greater or equal to 0 from one side. And from the other side, if we take this limit at infinity, using the fact that this one is strictly positive, we deduce that the energy is coercive, but with respect to the Neha manifold, restricted to the Neha manifold. Very well. Another auxiliary result shows that for any lambda strictly bigger than our crucial value beta lambda 1, any minimizing sequence of the energy is in fact bounded. This is very important because it opens the paths to the methods of the calculus of variations. This will imply immediately that M lambda is strictly bigger than 0, so the infimum is not associated with the possible trivial solution. The infimum is strictly positive, and then we conclude the proof by showing that for any lambda bigger than beta lambda 1, there is indeed some U lambda hat in the Neha manifold such that the minimum is achieved on this value. So this means in fact that U lambda hat is a solution. So the proof is done. These are the main the main steps of the proof in this situation, which corresponds to the isotropic case. Now, what happens in the anisotropic case? I shall start, in order to explain better what is this problem with mixed regime. I shall start from the standard, the classical Lane-Emden problem, which is stated here in the Quasi-linear framework. So this is the equation minus p Laplace of u equals modulus of u to q minus 2u in omega, the same, omega bounded with smooth boundary open and so on, with u equals to 0 on the boundary. The existence and the non-existence of solutions of this classical problem strongly, essentially depends on the values of q with respect to the Sobolev critical exponent of p. P star, the Sobolev critical exponent, is defined as n, the dimension of the space, times p over n minus p, if p less than n, plus infinity otherwise. What happens? We can distinguish only one of the following three situations. The case where q is less than p star, this corresponds to the subcritical case. Everything here is very well known. We distinguish other three subcases. For instance, in this situation, if q is less than p, that the energy function is coercive, so absolutely no problem again. If q is bigger than p, the energy satisfies the mountain pass geometry of Ambrosetti and Rabinovich, plus the compactness condition, for instance, Palais, Mail, or Cerami, and so on. So the problem has a solution by the Ambrosetti-Rabinovich theorem, while the remaining case p equals q corresponds to an eigenvalue problem, so we can have or not solutions. The case q equals p star was studied starting with the pioneering papers by Brezis and Nirenberg. In this situation, the topology of the domain omega plays a crucial role. For instance, there are some cases, one of them is illustrated here. This is a critical case in dimension 3. In this situation, we can have a positive solution for our problem. The last situation, the supercritical case, corresponds to q strictly bigger than the Sobolev critical exponent of p. Here we can have or not solutions. For instance, a very well-known case of star-shaped domains was studied by Pohozaev. So by Pohozaev identity, we do not have any solutions. Otherwise, for instance, if omega is an annulus, the problem can always have a solution and always has a solution, and so on and so on. So results of this type were established at the beginning by Barry and Coron and others. This situation is difficult, is very difficult. So in the case of constant exponents, p and q, we can distinguish one of the three different situations. The blue region corresponds to the subcritical case. The red straight line corresponds to the critical Sobolev exponent, while the green region corresponds to the supercritical case. So with our problem, we can be only in one of these three situations. There are no other situations in the case of constant exponents. So let us say in the isotropic case. Now, what happens if we replace p and q by functions p of x and q of x? So variable exponents we have in this situation. The associated Lane-Emden equation is this one minus px Laplace of u equals modulus of u to qx minus 2u in omega, again with u equals to 0. But the new differential operator has a very difficult structure. This is non-homogeneous and has many very interesting and new properties. The structure is extremely complicated. This is the px Laplace operator. In this situation, again, the critical exponent of P of X plays a crucial role for the existence of solutions. This is defined here, but we observe that this time, this is not a constant, a real number. It is a function depending on X. I shall give you an example. For instance, this parametric lane Emden equation, just to give some ideas, what happens in this situation where lambda is a positive parameter. This is an example to illustrate what happens. You observe that one of the hypotheses shows that the minimum of P of X, which is associated with the source term, is strictly between the minimum and the maximum of Q. We observe that an hypothesis of this one cannot take place in the case of constant exponent, because in this situation, the minimum equals the maximum of Q. Also, at the same time, due to this hypothesis, it is worth to point out that the energy functional is not coercive, doesn't satisfy the Ambrosetti-Rabinowitz theorem. So it doesn't have a mountain pass geometry. So this is the first assumption. And the second assumption shows, in fact, that our problem is subcritical for any point in omega. So at any point, our problem is subcritical. In this situation, we can prove a partial result, but very interesting, namely that our problem number 8 has a solution for small perturbations of the right-hand side. Namely, there is some lambda star positive such that our problem has a solution for any lambda positive but less than lambda star. What happens over lambda star? Everything depends on the values of P of X and Q of X. But looking again at hypothesis H2, which shows that the problem is subcritical at any point, we observe that it is possible to write the domain omega as a union of some subdomains omega 1, omega 2, and omega 3, such that our problem is subcritical in omega 1, it is critical in omega 2, and it is supercritical in omega 3. In this situation, our problem becomes a problem with mixed regime, with triple regime in this situation, more precisely, subcritical, critical, and supercritical. In this situation, you see the diagram is the following one. Again, the blue region corresponds to the subcritical region. The curve P star of X, which is no longer a straight line, this is a critical Sobolev exponent, while the green region corresponds to the supercritical case. So we observe here, we have an example showing that in some points of omega, our problem is subcritical, becomes critical here, again subcritical, critical, supercritical, and so on and so on. So this is just to illustrate what happens, the situation becomes completely different. So this is a problem with mixed regime. I point out that here there are plenty of open problems. I shall give you only 3 existence results. In the radial case, the first one, in the non-radial case, the second one, and in the singular case. In fact, I shall consider in all the cases a double phase problem, always with variable exponent, and there are several variable exponents. So since we are in the radial case, we shall assume at the very beginning that omega is a ball. The first variable exponent is denoted by P. They will appear immediately in the expression of the differential operators and of the right-hand side. M is a second variable exponent. These hypotheses are very natural. A of X is a potential, but we can assume that A is a constant. For instance, A equals to 1, just to not complicate the things. But it is important to point out that here P, A, and Q are assumed to be symmetric, to be radial functions. so to be radial functions. This is a first basic hypothesis. Also, we have another variable exponent denoted by Q, assumed to be non-negative. But here it is important to mention that this assumption denoted by H4 shows that Q satisfies a subcritical assumption, but not globally, only with respect to a small ball. So we start from the ball of radius capital R, and we have a small region, say the ball of radius small r, such that our problem is subcritical. So we start with something which is subcritical, but we don't know what happens outside this small ball. This is very important to point out. So this is Q, which is subcritical somewhere. Very well. So this means that Q can be critical, supercritical, any behavior. Here I have given several embeddings which are known because we are in the case of the ball, we are interested to use a space of radial functions. We have, for instance, this compact embedding, which is due to Strauss, and so on and so on. Also, we have other embeddings here. Always it is interesting to point, it is important to point out that these embeddings hold for radial functions. And also I have denoted here the Sobolev space W1px with respect to symmetric functions. So these are the functions in W1px such that these functions have a radial symmetry almost everywhere in the ball. We also have this compact embedding, which is stated here, always with respect to radial functions. Now I shall define the differential operator, one of the differential operators which appears in our problem. So this is the mx Laplace operator modulated by this potential A of x. But as I said at the beginning, we can assume that A equals to 1 to not complicate the things. The function space where we work is a standard Sobolev space with variable exponent px with 0 on the boundary, intersected with the W1mx with respect to the weight ax and 0. This one is associated to this new differential operator. So this is a first question. So we have considered this function space. So what happens if we take into account other function spaces? But this is just an example, as I said. There are plenty of directions to develop here. Here we have the so-called Luxembourg norm. We observe that this one is very difficult to manipulate, extremely difficult. Anyway, our function space denoted by E is considered with respect to the norm which is given here. Good, so we have these embeddings. The problem I shall consider is this one. So minus px Laplace of u minus this new operator equals the same. This is a Lane-Emden right-hand side. Under these assumptions, this problem has at least one non-trivial solution. So this is a main result in this direction, the main existence result. The basic tool in the proof is the Palais principle of symmetric criticality, which says more or less in a popular form that critical symmetric points are symmetric critical points. And the rigorous statement of the Palais principle is given here. So the problem has a variational structure. So we associate the energy, which is defined here. The first difficulty is that the energy is not well defined with respect to the whole space because of the last term. This one has a subcritical growth only with respect to a small region, but otherwise we don't know the ball, the behavior outside this ball. So we shall restrict the first idea to restrict the energy with respect to the radial functions. Here we are in the one-dimensional case. In fact, we have good properties. We have mountain pass, Palais mail, so we can apply mountain pass to find a non-trivial critical point with respect to the space of radial functions. Here it is not possible to apply directly the Palais principle because our energy is not well defined in the whole space. That is why we shall use another trick, namely we take a truncation of the right-hand side, which is defined here. The new function has a subcritical growth. This is very important to point out. And we consider an auxiliary problem, which is given here. This one doesn't have any difficulties. Due to the fact that J is subcritical, we can apply the standard methods and we obtain the existence of a critical point. And after observing that the right-hand side, the truncation coincides with the given nonlinearity with variable exponent, now only at this moment we can apply the Palais principle to obtain the existence of a non-trivial critical point with respect to the whole space. So this is the first result. The second result corresponds to the non-radial case. The main difference, very important difference, is that omega is a general domain, not necessarily the ball. Here I gave again the hypothesis. I shall point out only the differences. Here, P and Q, of course, it is not possible to have global symmetry assumptions. They have local symmetry assumptions with respect to some small region, say some small annuls. Again, a local subcritical assumption about Q, and under these assumptions, our problem has at least one non-trivial solution. Of course, here it is not possible to apply as until now the Palais principle because we are not on the case of the balls. But the main idea is to look locally on small with respect to small balls and to obtain local information, then to collect the local information and to find a global result, namely the existence of a non-trivial solution. I shall conclude with a singular case. This means the following: we keep the left-hand side of the Lane-Emden equation. In the right-hand side, we keep the same nonlinearity, but we shall consider also a parameter. So this is a parameter problem. And here the difference is that the problem becomes singular. Why? Because we shall assume that Q vanishes on the boundary. So since Q vanishes on the boundary, what happens on the boundary due to the fact that Q equals to 0? The right-hand side of our equation equals to plus infinity. So the problem becomes singular on the boundary. Here, there are the main hypotheses. In this situation, what it is important, as I said to you, hypothesis H12, this means that the potential which describes the right-hand side vanishes on the boundary of the domain omega. Under these assumptions, we can prove even more, namely that our problem has at least two non-trivial solutions. But there is a price to pay. This doesn't happen for any lambda. This happens only for small perturbations. So again, there is some lambda star positive such that our problem has at least two non-trivial solutions, provided that lambda is between 0 and lambda star. Again, the sketch of the proof. Here we associate another closed subspace of our initial function space E, and we shall consider the energy with respect to the subspace X, which is in fact a space of radial functions, but locally with respect to some ring, to some annulus. There are some preliminary results. You see, this one shows the existence of a mountain. This one shows the existence of a valley, but we don't have information about the location of the valley. So this is a very difficult situation. That is why we cannot apply mountain pass, but by Eklund, we can deduce the existence of a critical point. And then by other arguments, and finally, in fact, we obtain the existence of two different solutions, which are not trivial due to the fact that the corresponding energy levels are strictly positive or strictly negative. And this is the end of the proof in this situation. Some open problems. Here I have described what happens for anisotropic equations with the variable exponent. I don't know what happens for the Bauer-Grushin operator. If we replace P Laplace operator, Q Laplace operator with this elliptic hyperbolic operator, also biharmonic problems and so on. Here for heat equations with mixed regime, there are some results of Claudiano-Alves. And also it is very interesting to study different classes of non-local problems. For instance, Kirchhoff problems, Shokar problems, and so on. As I said, until now, the first part of my talk is included in this paper with Papageorgiou and Repos, and the second one in this paper with Alves, both published in the Proceedings of the American Mathematical Society. Here I have mentioned other papers about double phase problems. There are plenty of very interesting contributions, and I would like to use in a clever way the time you gave to me, and I am pleased to say thank you very much for your attention and for inviting me.
Thank you, Vicentiu. A very nice talk. So I learned a lot about these things. So any questions, comments? You can open your microphones if you prefer to talk, or maybe you can chat.
I have one question, Damian.
Okay, good. Diego?
So, Professor, in your study, you have considered just a Dirichlet boundary condition.
Yes.
What happened in other kind of boundary condition, like Neumann?
This is a very interesting question. You see, I have started from the classical problems. The classical eigenvalue problem in both cases corresponds to Dirichlet. What happens? This is a very interesting direction. I haven't studied Neumann or Robin, but at least Neumann I haven't studied. But as I said, there are plenty of new directions to consider similar problems. Absolutely, the arguments do not remain valid, but maybe some of them, we can keep some of them, but this is an invitation for the future. Absolutely very interesting open problem. Thank you very much.
Welcome. And I have another question. It's related with your list of open problems. You mentioned the Grushin,
Yes.
a kind of Grushin operator, no?
Yes.
Do you have any idea in the 1D case with degenerate elliptical equation? For instance, yes, when you have...
One case, you see, without variable exponents, in fact, more or less, we obtain the trichomy equation. The trichomy equation in the one-dimensional case, the Bauer-Grushin operator. But here you see it is much more complicated because here we have a variable exponent, g, depending on x and y. And the main idea is to study problems with mixed regime. So again, with mixed regime, as in the second part of my talk, but replacing the standard here. Usually, until now, we had the P Laplace operator and here the Q Laplace with x, depending on x. So what happens here? You see, we don't have an elliptic operator. The structure is completely different because of the on the hyperplane where x vanishes, this one disappears. So we have a hyperbolic operator, absolutely a different structure. I was interested in some papers about the Bauer-Grushin operator, and I found many difficulties. But I know on the other side, there are plenty of applications of operators of this type. For instance, transonic flow. Transonic flow is described exactly by the Bauer-Grushin operator. And also I refer to the very important paper of Kathleen Moravec, who studied operators of this type, but without the variable exponent. Here she considered constant exponents.
Okay.
Very, very interesting direction. Bauer-Grushin is extremely important. There are a lot of motivations.
Okay, thank you. Thank you.
Thank you.
So, other comments, questions? So, Vicentiu, I have one, maybe two questions. So, what happened? Maybe I don't know about the literature about the case when we let p goes to infinity. So,
yes, here, yes, indeed. I haven't studied this situation. This is very interesting. Very, very interesting situations to obtain solutions of another type and so on. But you see, until now, I was interested only in new phenomena, which appear due to the presence of two different differential operators. To study the asymptotic behavior, yes, this is another direction. I was not interested here. But I'm sure that this is complicated. This is, but for sure, it should be some relationship between the limiting case and what happens here, for sure. But I do not know for the moment. It would be very interesting. You see, I have pointed only the existence of a discontinuity property of the spectrum. The spectrum is an open interval, so which is no longer isolated as until now due to the first eigenvalue. So, but this is a new phenomenon. But what happens at infinity? This is another very interesting open problem. As I said, if A, alpha, and beta are not necessarily both positive, if one, for instance, is positive, the other one is negative, what is the strongest one? What is the exponent which decides the existence or non-existence of solutions, and so on? Thank you very much.
So, other questions, comments? So, Professor Vicentiu, I was thinking about, you mentioned about the problem when you have three regions, right? When,
yes.
Okay, you have subcritical and supercritical. So is there any result when you forget about the worst one and start the model allowing to have only two regions? So maybe you can improve results, maybe something like this.
See, in this approach, it is possible to have three regions. It is absolutely no problem. But it is important to start somewhere, to be sure that somewhere we have a subcritical behavior. If we don't have any idea, if we have problems only with critical and supercritical behavior, this is also a problem with double regime. We cannot say. I am afraid that this is absolutely very difficult. So if we are here, but if we start somewhere, even a very small region where the problem is subcritical, we can do several things. But otherwise, if we don't have this information, we start from subcritical, it seems to be extremely, extremely difficult. And also, this depends on the values of P of X, Q of X, again, which is the strongest one, and so on. So, several unknown facts, yes.
Okay, good. So, nice, because I'm thinking about things like that these models. So I was wondering something like if you consider an equation, right? So px Laplacian u equals to 0, but p changes according to the sign of u. So maybe something like this.
Yes, this is another approach, but very difficult, I'm afraid.
So is there any article, maybe just reference about this model? No, maybe not.
Right? I don't know, but it seems to be very delicate situation.
Yes. Good. So thank you, Vicentiu.
Thank you very much to you.
It was a
pleasure. Thank you very much.
So Diego?
Yes, so thank you, Professor Vicentiu, for this wonderful talk. So with that, we finish our first part of our